Along with logarithms come a bunch of properties of logarithms. These can be very tricky to keep track of, but my mental trick is to associate each property of logarithms with the corresponding law of exponents. So this product to sum property for logarithms says that if you have a product inside a log, it's like having a sum outside of a log. And the way that I remember that is, usually it's easier to remember the exponential laws. It's just people are more familiar with them usually, right? Which looks like this. Well, so for this one, a product outside is a sum inside. Notice that the corresponding logarithm law is just the other way around. It's a sum outside and a product inside. That's not a coincidence. This is basically a reflection of the fact that logarithm base a is the inverse function for exponentiation base a. So really, these are two sides of the same coin. Corresponding to the fact that a to the n over a to the m is a to the n minus m. Right here we have a quotient outside and a difference inside. So the corresponding fact for logarithms has a difference outside and a quotient inside. For exponents, this one is not as obviously related to the corresponding fact for exponents. In fact, it is, but it's not as clear to see. So this would be a to the n times m. Right? So here n is sort of playing the role of log base b. So it turns out to prove this fact about logarithms, you do basically just turn this fact about exponents into a log fact, but it's not as tidy as for the previous two. One student of mine described this as rolling the exponent off the log. Right? Of course, it works backwards. You can also take a coefficient in front and roll it back into the log. One thing to be careful of is that if this exponent isn't inside the logarithm, you can't move it. It's stuck out here, right? Because this exponent isn't inside the log. Another thing to be careful about is if this what makes this work is that the logarithm sort of is sitting at these parentheses, and the first thing that it sees is this exponent, right? If the exponent isn't the first thing that it sees, you can't do anything, right? So for this example, the logarithm doesn't see this exponent. What it sees is the last operation that happens inside these parentheses, and that's the sum, right? So this logarithm really only sees the sum. And what logarithm law is there for sums? Well, there isn't one, so you can't mess with this. You're stuck with this expression. There's no way to rewrite it. All right, the last fact about logarithms doesn't have an obvious corresponding fact with exponents. There is a corresponding fact with exponents, but it's actually not very illuminating to write down, so I won't. But it's the change of base formula, which says that log base a of b, you can choose any new base you want, and you can rewrite this log base a in terms of log base c. So it turns out it's log base c of b divided by log base c of a. This is very handy because if you look at if you look at a scientific calculator, most of them only have two logarithm buttons, natural log and log base 10, which remember is common logarithm. So how do you compute logarithms for other bases? Well, you always change your base to either base e or base 10, right? So you don't really need a logarithm button for every base. You really only need a logarithm for one base. So, having two buttons is sort of extravagant because you really only need one. The reason there are two is because natural log is sort of the most important logarithm mathematically speaking, so we need a logarithm button or a natural log button for that reason. And for science and engineering, having powers of 10 around is so common that log base 10 is often something that you want to calculate, and so it's nice to have a button for that. Other logarithms aren't as commonly needed, and so they don't have a button dedicated to them. All right, let's look at some examples of how we can use these laws of logarithms. There are lots of ways to use these facts about logarithms, but it turns out for what's coming down the road when you start learning calculus, there are two main things that you'll need to do with logarithms, and that is to turn messy logs into simple logs and to turn sums of logs into a single logarithm. So the situation here is much like factoring a polynomial. With a polynomial, do you want it factored or do you want it multiplied out? It depends on what you're doing. The situation is the same here. If you have a log like this, would you rather have a log like this? Or would you rather leave it the way it is? It's sort of not really clear. It depends on what you're doing. So sometimes you would want to leave a single logarithm alone, but sometimes you'd want to break it down into simpler pieces. And sometimes you'd want to do the reverse. It just depends on what you're doing. So let's just see how this works out. So let's expand this single complicated logarithm into multiple simple logarithms. When I say simple, what I mean is let's rewrite it so that the stuff inside of each logarithm is as simple as possible. All right, well, a logarithm sees the last operation inside of it, and that's the quotient. So we can use the quotient rule for logarithms. So this is log base 3 of the stuff upstairs, which is 3x squared times y cubed, minus log base 3 of the stuff downstairs, which is z to the 6th. Okay, now working on this logarithm, it's a product. So we can use the product to sum rule for logarithms. So this is log base 3 of 3 plus log base 3 of x squared plus log base 3 of y cubed. Okay, and then minus log base 3 of z to the 6th. Now there are a couple things we can do. So first of all, for this first piece, log base 3 of 3, remember logarithm base 3 pulls out the exponent on your 3, but that's a 1 here. So log base 3 of 3, that's 1. Plus, now log base 3 of x squared, right? The first thing this logarithm sees is the last operation inside, but that's the exponent. So we can use our exponent rule and move this 2 down here. So 2 log base 3 of x. And then we can do that for the other logarithms as well. So plus 3 log base 3 of y minus 6 log base 3 of z. Okay, and now this is as simple as we're going to be able to get these inside pieces to be, right? Because each piece is just a single variable. So there's no more simplifying, there's no more rearranging we can do to make these insides simpler. So we're done. All right, of course we can do this in the reverse. If you have several logarithms with the same base, you can often put them together. So because these are added and subtracted, right, eventually we'll use the sum and difference rules for logarithms, but there are these coefficients in the way, right? If you look back at our, for example, our sum rule for logarithms, right, it says that a product inside is like a sum outside, like this. This doesn't have any coefficients in front of our logarithms. So before we can use the sum to product rule for logarithms, we need to move this 2 and this 3 somewhere else. Well, where else can we put them? We need to move them somewhere where they aren't going to get in the way of using the sum rule. Well, remember, we can put them inside the logarithms in an exponent. So this is 2 times. This 2 outside, we could distribute it through this sum, but we might as well leave it all the way out here. Okay, so putting these coefficients inside our logarithms, we get log base 5 of x plus log base 5 of y squared minus log base 5 of z cubed. Okay. Now that these coefficients are out of the way, now we can put these two together using the sum rule. So log base 5 of x times y squared minus log base 5 of z cubed. And now we can use the difference rule. So 2 times log base 5 of, so this is going to be a big fraction, x y squared, and then in the denominator is the stuff that coming from the log that has a negative, z cubed. All right, now if we wanted to, we could go a step further. Whether this is necessary or not really depends on what the larger context of where this expression came from. But if we wanted to, we could also move this 2 inside there. That would give us log base 5 of xy squared over z cubed all squared. And then we could rewrite this as log base 5 of, right, this square is going to jump onto each piece. So we get x squared y to the 4th over z to the 6th. All right, so we've rewritten this sum and difference of logarithms using a single logarithm.